Thanks. So my name is Daan Keuper. I'm the head of security research at Computest, a security company here in the Netherlands, doing everything from pen testing to incident response. And today I would like to talk to you about our latest Pwn2Own submission, which was last October, where we demonstrated what we call a SOHO smash-up, meaning we first compromised the router, and from there, from the WAN side, and then pivoted to a NAS on the LAN side. For people who are unfamiliar with Pwn2Own, it's a competition held a couple of times per year. They write out a list of targets, and you can participate by demonstrating 0 days vulnerabilities during the competition. They must be true 0 days. So after you demonstrate it, you can hack one of their devices. You are put in a disclosure room. You have to give full disclosure. They will check with the vendor, and if it's indeed a true 0 day, you can get a cash reward. This specific edition of Pwn2Own is all about IoT devices. So you have routers, printers, IP cameras, and whatnot. We decided to enter in the SOHO category, which came about because we first tried to find some vulnerabilities in a NAS. Specifically the TrueNAS Mini X. This was one of the targets selected by the competition leaders. Not sure why it's called a mini, because the thing is pretty big. It has seven bays. It's also quite expensive, $1,100. We never actually bought this one. The first time we actually saw the device in real life was during the competition. The price is the purchasing price is pretty high, so we thought, okay, let's first see if we can find vulnerabilities on the firmware, and then later purchase the device to see if it actually works in real life. However, at the moment that we were done with the full chain, these devices were out of stock, so we could no longer test it on a real device. So we went, well, it will probably also work in real life. Let's just let's wing it. So the device itself runs TrueNAS Core, which is a FreeBSD-based system with, some software pre-installed. You can download it. It's free software. They nowadays also have a Debian variant, but this one came with the TrueNAS Core. It works perfectly fine in a VM. It's also meant to run in a VM, so you can run this on your own machine if you would like. It's standard NAS software. It has everything you would expect from a NAS. You can enable Samba shares, AppleTalk shares, etc. And we looked around for a bit, and we noticed that if you have if you have access to the system, it automatically also means you have shell access. In the web interface, there's a very handy button to get a command prompt over WebSockets. So meaning that rather than finding something that leads to remote code execution, we can also focus on finding something that allows us to bypass authentication, because once we have a session, we can just use that WebSocket connection. So the first thing we did was start a packet capture to see what the outgoing connections were of this firewall. And this was something we noticed. It's an HTTP request, meaning we can easily intercept it, change it to something else. But at first we thought, okay, package.freebsd.org, this is most likely something FreeBSD internal, so not very likely that we can find vulnerabilities here. Until we noticed that the request header of the user agent here is actually Python requests, which is, well, weird if for a FreeBSD-based system. So we looked a bit closer, and it apparently is something that FreeNAS wrote themselves. It's called IOCage. It's a Python project to manage FreeBSD jails. So we looked through the source for a bit, and we found this file. This is how it extracts that tar file that it's downloading. And if you look in the documentation of extract all, it clearly mentions that you should never do this with untrusted sources, because the tar file can just contain // to write arbitrary files to arbitrary locations. So this was an easy win. basically what we did, we spoofed that DNS record, we serve a malicious tar file, we update the user credential database, and then we can just authenticate on the device, start that web shell, and be done. So this all took like, I don't know, 30 minutes or so. So we're like, okay, this is interesting, but this does require that you can spoof the DNS records. So you need man-in-the-middle capabilities, or you need to be the DNS server. And this typically is not allowed for Pwn2Own. Hey, typically if you want to compete with this NAS, then you are placed within the same network. And of course you can do ARP spoofing, etc. But typically man-in-the-middle attacks are not allowed unless you compete in the SOHO category. The SOHO category means that you first hack a router on the WAN side, and then you can pivot to any device on the LAN side. Well, if you're the router, you automatically have man-in-the-middle capabilities, meaning that this would be a perfect vulnerability for a SOHO smash-up. But that, of course, also meant that we needed to hack one of these routers in order to be able to compete. So we looked at some of those routers. There's a Ubiquiti in there, there's a Nest, a MikroTik, etc. Some have decent security reputations, like a Nest that's by Google, so it comes with the whole Google ecosystem. The Synology has been a target for many years, but the QNAP was quite new. It was the first time that it was selected as a target. So we're like, okay, let's go for the QNAP. So this is the device. It's apparently a secure networking router, apart from the fact that, apart from us, 7 other teams also found remotely exploitable vulnerabilities. So it pre-comes with at least 7 vulnerabilities that are exploitable on the WAN side. It was also one of the most expensive routers on the list. I think it costs 600, 700 euros or so. So it's quite expensive. So the first thing we thought, okay, we had some success with looking at outgoing traffic on the TrueNAS. Let's see if the same also works for this router. So there are a couple of outgoing connections, DHCP, of course, DNS, etc. These are all well-established open source projects. We're like, okay, we're not going to find vulnerabilities in here in the couple of weeks we have before the competition. And if so, we're not going to burn them on some crappy router on a random competition. So we skipped those. There were 2 outgoing connections from by QNAP software. The first one is Cloud Agent, which does a couple of TLS requests to the cloud, the QNAP cloud for remote configuration, etc. It does TLS. We checked, of course, if it correctly validates certificates, and it does. The other daemon was something called NCSID. It does an HTTP request, not TLS, and it grabs a text file. We're like, okay, it would be cool if we can do 2 man-in-the-middle vulnerabilities at one competition, both over HTTP. But apparently what it does is it tries to grab that text file, and then it does a regular expression over the headers to see if it gets a 200 and if the content length is of the correct size. And if so, it determines that it has internet connectivity. The body of the message is completely ignored. It's written to dev null, and none of the other headers are parsed unless you know vulnerability in curl itself. So there were no outgoing connections that were of interest to us. Let's look at the listening services. Well, there is some TCP service listening on all interfaces, but the default firewall configuration blocks all of them, so they're not accessible for us. And there are 2 UDP services listening. The first is Sharon. I'm not sure if it's everybody knows this one, but it's a standard IPsec implementation. So we also decided to not dig further into this one. But there's another service listening specific to QNAP, namely Q1WMD. No idea what it stands for or what it does. We reversed it for a bit, This is the protocol. You send it some JSON. It needs to have a sender, a receiver, and a WAN field. And if you send this, you will get some information back about the memory usage, the CPU usage, etc. I have no idea why this is listening publicly on your router, but apparently it is. There are some quirks, like some things need to be an integer. If it's a string, then it will bail out. It will trigger an assertion fail. But in the end, we didn't really find any vulnerabilities here, unless we would maybe dig deeper in that JSON parser. Maybe that one was flawed. We were like, okay, let's try to increase our attack surface. Let's see what we can do. Well, there's a lot of you can do, of course. You can, of course, hand out IPv6 addresses. See if maybe the listening ports are different on IPv6 and on IPv4. We could focus on data that is transferred from WAN to client sides and look for parsing errors there. You could try various state changes, only handing out IPv6, dropping packets midway, alter specific packets, just to see if we can push that router in some alternative state that would allow us to find some more vulnerabilities. And then basically just observe the results, rinse and repeat, unless you have a vulnerability that, that favors you. This is, of course, also very error-prone. Some other teams noticed that on IPv6, the web interface was also available. I tried this on my device, but it didn't work. I have no idea. There's some state change why this, why the port is open or why it isn't open. So this is very error-prone, and of course there are a lot of things you can alter on the state of the device to see if you can create some more attack surface. For example, one of the things we found was that there is a service listening on a very particular IP address, and that IP address is bound by a TUN interface. But we were like, what happens if we hand out this IP address over DHCP to the WAN side? What then happens? Well, it turns out that then suddenly that port is also accessible for on the WAN side. So cool, some new attack surface. Let's dive a bit deeper to see if we can find some vulnerabilities here. Apparently this service is part of this RFC. And it's a benchmarking technology for internet connectivity. And basically what it does, it reads data in a buffer, a fixed size buffer, and it does that in a loop with correct error checking or bounce checking, unfortunately. But that buffer is never actually used. So it's just continuously receiving data in a buffer and then rinse and repeat. But what it does, it tries to determine the transfer speed. So the data that we send is actually never parsed. So from a bug hunting perspective, this was a dead end. So okay, we have some more attack surface, but not enough for us to actually find some vulnerabilities. We decided to look at the DHCP requests that the device makes one more time. And then we noticed one strange request. I'm not sure if anybody here noticed it because it's easily overlooked. Anyone? So it does a quadruple A request for localhost. Which is strange. Typically, you have an entry for this in your etc host file. And it turned out that the QNAP does have one for IPv4, but it doesn't for IPv6, meaning that some services, once you try to resolve something on localhost, it will actually do a DNS request to the outside DNS server to see what the IP address for localhost is. So we're like, cool. What if we respond to this with an IP address of our own, and then just look for incoming packets to see if we actually receive some data. Well, turns out there are two services that actually try to connect and that now send traffic to our server. One HTTP request and one gRPC request. So, cool. This is new attack surface. Most likely it's unintended that this traffic ever leaves the device. So that makes it interesting attack surface for us. And we decided to first look at the HTTP request, because that's of course easily to mock up and try to find vulnerabilities in. So a service DM agent is responsible for this request. It uses curl to make this request that actually does the DNS resolving. And it tries to resolve, or it tries to reach RapidD, which is some database. And it expects a JSON list of response with a list of connected devices. And it looks very exploitable. So this is how that JSON response should look like. It's basically every client, its OS, its model name, its MAC address, etc. So we can spoof this response. We can send anything we want. So we thought, okay, how is this data actually parsed? Well, it turns out they use a whole lot of string copies for this, which are not bound checked. These are unsafe by default. So by just sending a large MAC address or a model name or whatever, we could easily overflow data on the easy overflow memory. So it copies each element to a heap struct one by one. It's an array of objects, so we can send multiple objects, like multiple connected clients, and it will parse them one by one, so we can reach that string copy many times. And actually, the MAC address field is later used in a call to Pwn2Own. So we could actually inject shell commands here. There are some pitfalls. It first has a sleep of 5 minutes, and during Pwn2Own, you're on a clock. You have 10 minutes per attempt. So if you have to if you have to wait for 5 minutes, and you also have to hack the true NAS in that 10 minutes, it's not ideal. But most importantly, the format is limited to a typical MAC address. We can inject any character we want, but it will include that semicolons at specific locations. So we thought, okay, can we use that string copy to overwrite the MAC address that will then be used in Pwn2Own? The problem with this is that it is at the very beginning of the struct. It's stored in memory. So it will first store the MAC address and then the OS name and all the other fields. So with the string copy, we cannot directly overwrite a MAC address because that will be placed in memory before the things we can overflow. So maybe we can overflow one in the next device or next connected client. I have an illustration. Like, suppose this is an empty heap. It will first allocate device number 1 with arbitrary data, which of course we can overflow in the next heap element. The problem is there is nothing there at that moment, because then it will parse the second device, and then it will allocate that on that location, overwriting the bytes that we have just written to memory. So typically what you would do is what we call heap shaping, where you make sure that you control the structure of the heap. For example, if there is some random data on the heap, and we could make the allocation of device 1 here, and we could then somehow deallocate one of those chunks before this device, and then we trigger the buffer overflow. Then we could overwrite the MAC address of the first device, and then we could inject arbitrary system commands. There were some problems with this idea. The first is certain fields need to be 0 for this to work. And we cannot really write zeros because we're in a string copy. If the string contains a 0 byte, the string copy will immediately bail out. But maybe we can use the fact that we have multiple string copies to make this work. And how that would work is, so for the first string copy, we just write arbitrary number of A's. The string will always be null terminated because that is what C does. Suppose that the orange A's needs to be null for our attack to work. What we then could do is use the second string copy to overwrite some B's and then make sure that the terminating null byte is exactly at the place we want it to be, and rinse and repeat for the third string copy. This was the idea. It would work in practice. We tried some heap shaping with HTTP headers, JSON fields, etc. But it does turn out to be quite more difficult than we initially anticipated. We also needed more null bytes than we had, strict copies, and QNAP kept pushing patches. And every patch could mess up the heap layout that we were currently working with. This is the release, QNAP release page right before the competition. Typically, this means that other teams are also looking at this target, and they're trying to burn 0 days they have, so that people cannot use them during the competition, and they have the advantage, because all the release notes only mention, well, you have multiple security updates have been patched. Okay, so let's look at the second connection. It's a gRPC connection. It's made by some service that tries to connect to cloud agents to get information about the cloud configuration. So we dumped the original traffic, create a mockup, etc. There are multiple types of messages being exchanged. Some are only a single bit long, or some are only a single string. But one expected some JSON with something that's called a site info. This is a standard payload on our device. So it retrieves this JSON file over gRPC, and first we thought the layman's approach just includes shells of a system command everywhere, just see if this works. Unfortunately, it didn't. It's a little bit more complex than this. It writes contents to a file on disk. Another process will read this. That will execute a Python script. That will check for modification. And based on modifications, it will send out various IPC message. So this is the actual flow. But of course, gRPC handler is no longer communicating with Cloud Agent. It actually communicates with us. Well, maybe this is a more appropriate, because we have no idea what we're doing. We're just YOLOing this. So we decided, okay, we need to look at that Python script, because based on the Python script, it will trigger other services over IPC. The problem is that the Python script is compiled Python. You can decompile it, of course, but it's not really human readable. It's very complex on parsing the entire site.json to see if we can, to see if it can find modifications. So we just pinpointed something on the map, like, okay, on this line number, it calls this service over IPC. I have no idea what this does, how it works, etc. But for let's just try to see if we can make this IPC call happen. So can we create a site.json with enough modifications that this IPC message is being sent? So we picked one at random. We reversed the Python script until we could generate a valid site.json, and then we use strace to see if the receiver of this message does anything interesting with this message. And apparently we got lucky on the first try. This is the payload. There are a couple of things in this site.json which make it unique, which is non-default, but after that, it's just straight up command injection. And by using strace, we could see this being executed in a shell. So I have a demo movie of this attack in practice. So left side is the QNAP exploit. We're going to first run this one. It acts as a DNS DHCP server. We get a new QNAP router that connects to us. We'll wait for the localhost DNS request. If that happens, we wait for incoming gRPC messages. And if we have a gRPC message, then we trigger the updated site.json and we get a shell. From here, we can pivot to the true NAS. That's basically waiting for a request to freebsd.org, overrating the site.json, and then authenticating ourselves over the web shell. And we have a shell. So this is this is basically what we demonstrated during the competition. We thought we got very unlucky in the drawing, because if multiple teams register for the same target, you get a drawing, and yeah, you want to be first in line, of course, because that gives you more chance that your bugs are unique. We were 7th in line out of 7. So we were like, okay, no way that these bugs are unique, especially the TrueNAS bug. Like, that is so shallow that other teams must have found this one as well. But apparently, both of our bugs were unique, were not duplicates. So I'm very interested to see what all the other vulnerabilities of the other teams are. Apparently, they're riddled with bugs. If you want to know more details, you could read our write-up. It's currently not online yet. It will be within a week or so. Just scan the QR code, you go to our blog. You can also find all of our write-ups of previous Pwn2Own attempts there. And this one will be there in the next week or so. Thanks.
And thank you, Daan Keuper.
Thanks.
Keuper, sorry. Are there any questions from the audience? We have about 5 minutes.
Is this thing on? Yeah, it's on. So how did you enforce the querying, or was that the local host call to gRPC? Is that like a
it's a scheduled thing? Yeah.
Okay, cool.
So we saw that multiple times. It does depend on the configuration. Like, we noticed that if we only gave out IPv6, it would come faster than if we also handed out IPv4. I think it will raise then, because then it can also reach the servers over IPv4. And it also depends if it had internet connectivity or not. But with the right configuration, you get that in like 3 seconds after connectivity.
And the control over if it has internet, if it has IPv6, that's part of Pwn2Own. You can just have that.
Yeah, if you participate in this category, your laptop is directly connected to the WAN port of the router. So you have full control over the internet side. Yes.
Thanks.
We still have a few minutes left.
I see that Thijs has a question over there.
Sorry,
yes.
here.
Thijs.
No, it has already been answered.
Oh.
I have one comment and one question.
Yeah.
The comment is, it's not called a secure router.
Oh.
It was about the marketing material. It said that it provides a secure networking experience.
Okay.
Not sure.
I stand corrected.
I'm not sure.
I feel very safe.
Yeah. My question is, so what you did is you spoofed DHCP, or you provide your own DHCP on the WAN side.
Yeah, correct.
How likely is that to be a problem?
On the internet?
Because normally, I think the device would be directly attached to the provider router.
Yeah. I think from, if you purely look at the risk for arbitrary home consumer users, the risk is neglectable. There were some people that had some vulnerabilities that would actually work, I think, over the internet as well. But this one, you need to raise the DHCP server, but then you also need to know the query ID, etc., or the port number. I don't think this would be very exploitable over the internet, unless you have man-in-the-middle capabilities somewhere, which for some attack vectors might be a risk worth considering, but for the typical user, I guess this is not a real risk.
We still have some time. Any question?
So how much time did you spend researching this with the team? So put it in perspective.
Yeah, so the TrueNAS was, I think, 30 minutes or so, because it was the first thing we looked at. The QNAP, I think 1 or 2 weeks or so. Somewhere in that range, yeah. But we, of course, typically with research, you chase some errands, that some direction that ends up being nothing. It all depends on how lucky you are with your target selection. Like, okay, you're gonna target this service. You might find a vulnerability in no time. It could also be that you spent weeks on something like had a DM agent with that heap overflow. I'm pretty sure we could make it work somehow, but that would mean us to spend a lot of time on it. So we built out and chose a different target. But yeah, research always like a bit open-ended.
Did you consider giving up during the 2 weeks, or you were not at that point yet?
No, not yet. No, we had enough attack surface to cover to still make this feasible. No.
So if there's no questions left, I will ask for another big applause for
Thanks.
Daan Keuper.